October 21st, 2025. Something changed. Independent astronomers comparing live tracking data to NASA's official predictions noticed the impossible. 3I Atlas wasn't where it was supposed to be. Not by a few kilometers, not by 1,000, by over 1 million kilometers. And the gap was growing wider with every passing hour. The interstellar visitor that had been dominating headlines since July had done something no natural comet should be able to do. It accelerated ahead of its predicted gravitational path. 8 days later, it vanished behind the sun at the exact moment its velocity peaked, hidden from every telescope on Earth during the single most energy-efficient window for any spacecraft to execute a course change. Now, as it approaches perihelion, the object will remain invisible, shielded by solar glare, performing whatever it came here to do in complete darkness. When it reemerges in early November, we'll know if the deviation was an error in our calculations or if something out there just made a deliberate move. Tonight, we explore what happened during those 8 invisible days. We examine why planetary defense networks activated for an object that poses zero collision risk. We ask why the universe's coincidences are starting to feel a little too perfect. And we confront the uncomfortable possibility that we might be watching something far more intentional than ice and stone. The next 2 months will either confirm we're observing the most unusual comet in recorded history, or prove that warnings about alien technology weren't speculation at all. This is the story of an object that broke our predictions. And perhaps, just perhaps, the story of the moment when the universe noticed us back. In the vast darkness between stars, objects drift for millions of years. Frozen, silent, moving through the galactic disk at speeds that dwarf anything we can build. These are the interstellar wanderers, comets and asteroids ejected from their parent star systems by gravitational chaos, flung into the void to travel cosmic distances we can barely imagine. On July 9, 2025, astronomers detected one of these wanderers entering our solar system. The discovery came through the asteroid terrestrial impact last alert system Atlas, a network of telescopes designed to spot objects that might threaten Earth. The new arrival was designated 3I Atlas, the 3I marking it as only the third confirmed interstellar object humanity has ever detected, the Atlas naming it after the survey that found it first. Initial observations suggested something familiar, a comet. Spectroscopic analysis showed the chemical signatures we expect: water vapor, carbon dioxide, cyanogen. Imaging revealed a coma, that characteristic cloud of gas and dust surrounding the nucleus. A faint tail pointed away from the sun, pushed by radiation pressure and solar wind, exactly as comet tails should. By all appearances, this was what astronomers call a standard interstellar comet. Interesting because of where it came from, certainly, but not fundamentally different from the icy bodies we observe, originating from our own solar system's distant Oort cloud. Let's establish context. Before 3I Atlas, humanity had confirmed only 2 interstellar visitors. The first arrived in 2017. Oumuamua, Hawaiian for scout or messenger, appeared as an elongated object tumbling through space. It showed no coma, no tail, nothing that suggested active outgassing. Its trajectory was purely gravitational until it wasn't. As it departed, Oumuamua accelerated beyond what gravity alone could explain. The deviation was small but unmistakable. Something was pushing it. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard, proposed that Oumuamua might be artificial, perhaps a light sail, a thin reflective sheet pushed by radiation pressure. The idea generated enormous controversy. Most astronomers argued for natural explanations, asymmetric outgassing from ice deposits we couldn't see, or unusual rotation creating forces we hadn't fully calculated. The debate continues. The second visitor arrived in 2019. 2I Borisov looked exactly like what we expected an interstellar comet to be: active outgassing, clear coma, predictable behavior. It followed gravitational mechanics with no surprises. Astronomers studied it intensively, measuring its composition, tracking its trajectory, comparing it to solar system comets. The conclusion remarkably similar. If you hadn't known it came from interstellar space, you might have mistaken it for a local comet on a highly elliptical orbit. 2I Borisov restored confidence. Whatever Oumuamua was asteroid, comet, or something else entirely interstellar, visitors could be understood within our existing frameworks. The universe made sense again. Then came 3I Atlas. At first it seemed to confirm the pattern established by Borisov. Here was an active comet showing all the right characteristics. Scientists relaxed. Telescopes pointed. Observation campaigns coordinated. This was going to be a textbook case study. An interstellar comet, compare its chemistry to our solar system's comets, learn about stellar formation conditions in whatever distant system birthed this traveler. But as observations accumulated through July and August, small oddities began appearing in the data. The composition was unusual. Too much carbon dioxide, not enough water, emission lines that didn't quite match expectations. The coma showed strange geometric patterns in some images, color separations that shouldn't exist in the chaotic environment of sublimating ice. And the trajectory was almost too perfect. Understand what that means. When an object approaches from interstellar space, it can arrive from any direction. The galaxy doesn't care about our solar system's organization. Most objects come in at random angles, high inclinations that cut across the ecliptic plane where our planets orbit. 3I Atlas approached within 5 degrees of the ecliptic. Its orbital plane was nearly aligned with Earth's. If you were designing a mission to explore a planetary system efficiently, that's exactly the trajectory you'd choose. Maximum access to planets with minimum fuel expenditure for course corrections. The odds of that alignment occurring by chance? About 2%, not impossible, but unusual enough to notice. More curious, the timing. 3I Atlas would pass close to Mars in October, Venus in November, Jupiter in March 2026, close approach to 3 major planets during a single pass through the inner solar system is rare.
The probability, roughly 5 in 100,000. Still, comets surprise us. They fragment, they brighten unexpectedly, they defy models. The history of astronomy is filled with comets that didn't behave as predicted. Perhaps 3I Atlas was simply adding another chapter to that history. This was the baseline we established through summer 2025, an unusual interstellar comet, worth watching carefully, but ultimately a natural phenomenon, ice and rock and frozen gases, obeying the ancient laws of thermodynamics and gravity. That certainty lasted until October 21st.
October 21st, 2025. AO2 Coordinated Universal Time. A handful of independent trackers running routine sky surveys noticed something odd when cross-referencing their observations against the Jet Propulsion Laboratory's Horizons system. 3I Atlas had drifted off course. Not the subtle drift you'd expect from measurement error or outgassing pressure. This was different. The object appeared ahead of where gravity alone should have placed it. Let's establish what that means. When you track any celestial body, satellite, asteroid, comet, you're essentially watching gravity's invisible hand guide it through space. The JPL Horizons system is one of the most sophisticated astronomical tools we have. Think of it as cosmic GPS, but instead of satellites broadcasting positions, it calculates where objects should be based on gravitational forces from the sun planets, even the subtle tug from Jupiter's mass, millions of kilometers away. These predictions are extraordinarily accurate. When Mars rovers land, when spacecraft perform flybys, when we track near-Earth asteroids, Horizons tells us where to look within margins, measured in meters, not kilometers. The system has been refined over decades. It accounts for relativity. It incorporates gravitational perturbations from every significant body in the solar system. It works. On that October morning, Horizons predicted 3I Atlas would be at right ascension 13 hours 46 minutes, 57.51 seconds. Declination 8 degrees, 15 arc minutes, 20.0 arc seconds. That's where NASA said the object would appear in the sky, but the observed data told a different story. Multiple independent tracking stations cross-referencing their measurements found the object at right ascension 13 hours, 47 minutes, 54.3 seconds. Declination 8 degrees, 21 arc minutes. For those who don't speak astronomical coordinates, let me translate. That's not a small discrepancy. At the distance, 3I Atlas was traveling roughly 2.38 astronomical units from Earth. That angular offset translated to approximately 1.1 million kilometers of lateral displacement. Let that sink in. 1 million kilometers, not ahead by seconds in its orbit. Ahead by the distance light travels in 3.5 seconds. Here's where it gets genuinely strange. When tracking systems show a mismatch between prediction and observation, the error typically appears in a specific direction. If your orbital data is outdated, the object appears behind where you expected it. Think of it like trying to hit a moving target with old information. You're always shooting where it was not where it is. Orbital mechanics has predictable patterns. Comets accelerate as they approach the sun, decelerate as they move away. Outgassing can create small, non-gravitational forces, tiny jets of vapor pushing the object slightly off course. All of this is well understood and documented in thousands of comet observations going back decades. But 3I Atlas appeared ahead of its predicted position, not behind. Ahead. That breaks the usual pattern completely. When an object shows up ahead of gravitational predictions, it suggests something is pushing it forward, adding energy to its motion. For a comet, that would require asymmetric outgassing pointed in exactly the right direction to accelerate the object along its trajectory. Possible, certainly. Comets can be unpredictable, but the timing here raises questions that are harder to dismiss. The group that first documented this deviation publicly goes by the name Earth Exists. They're not NASA. They're not affiliated with any major observatory. They're part of a growing network of citizen astronomers who've taken it upon themselves to track 3I Atlas independently using publicly available telescope data and sky survey archives. Some might dismiss amateur observations. These aren't kids with backyard telescopes. These are individuals with access to serious equipment, people who understand astrometry, orbital mechanics, photometry. They've been cross-checking their findings against multiple data sources, comparing images from different observatories, running their own calculations. According to their analysis released on October 22nd, the positional offset wasn't static, it was growing. 19 hours after the initial October 21st observation, they ran another positional analysis. The divergence had increased. They calculated the rate at roughly 0.23 arc minutes per hour, which at that distance translates to a lateral velocity change of nearly 4 kilometers per second. That's not drift. That's not measurement noise. That's a sustained deviation from the expected gravitational path. Let's put 4 kilometers per second in perspective. That's roughly 14,400 kilometers per hour. For reference, the fastest human-made spacecraft, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at perihelion. But that's falling toward the sun with massive gravitational assist. We're talking about lateral motion here, perpendicular to the main trajectory. A velocity change like that requires force. For a comet, that force would come from outgassing jets of sublimating ice, turning to vapor and pushing against the nucleus. But here's the problem. When comets outgas strongly enough to create measurable trajectory changes, they get bright. Very bright. You see massive plumes, extended tails, dramatic increases in magnitude. 3I Atlas was doing the opposite. JPL had predicted an apparent magnitude near 14.8. That's already faint, requiring decent amateur telescopes to observe. but actual readings showed the object at magnitude 15.1, about 26% dimmer than expected. This is backwards. If outgassing was strong enough to push the object 1 million kilometers off course, we should be seeing the brightest interstellar comet in history. Instead, it's dimmer than predicted, even though the James Webb Space Telescope confirmed it's losing about 25 kilograms of water every second. So we have an object that's deviating from its predicted path in a way that suggests forward thrust, while simultaneously appearing dimmer than it should, despite confirmed active outgassing. These facts don't reconcile easily with standard comet behavior. Some have suggested the nucleus is rotating in a way that hides the main active regions from Earth's view, possible but convenient. Others point to composition anomalies discovered later, the unusual nickel emissions, the remarkably low water content. Maybe this object's chemistry is so different from solar system comets that it behaves in ways we simply don't have models for. Also possible. Interstellar comets are rare. We've only studied 3. Perhaps our assumptions about how they should behave are just wrong. But then there's the third explanation. The one most mainstream astronomers won't touch publicly, but discuss privately. What if the deviation isn't random? What if something about 3I Atlas is capable of adjusting its trajectory, not through natural outgassing that happens to be pointed in a convenient direction, but through something more deliberate? Avi Loeb has been saying this for months, ranking the object at 4 out of 10 on his scale of potential technological origins. The accumulation of anomalies, he argues, pushes the probability of natural explanations below comfortable thresholds. Each oddity alone can be explained. All of them together start to look like a pattern. The tracking community isn't unified on this. Some groups have tried to reproduce the Earth exists findings and claim they can't confirm the same magnitude of deviation.
Others say their data shows similar trends, but attribute it to outdated orbital elements in the JPL database. Orbital elements are the mathematical parameters that define an object's path through space. They get refined as more observations come in. Maybe JPL's last update was October 10th, and by October 21st, those elements were stale enough to cause prediction errors. Except here's the thing. JPL updates orbital elements for near-Earth objects and significant comets regularly, especially for something as high-profile as 3I Atlas. The idea that they'd let the data go stale by 11 days during the approach to perihelion seems unlikely. This is exactly the period when tracking would be most critical, when observatories worldwide are pointing instruments at this object. When NASA has coordinated observations from Mars, orbiters, the Hubble Space Telescope, James Webb, and ground-based facilities across multiple continents. David Sarita, another independent researcher, added fuel to this particular fire on October 20th. He was reviewing images from NASA's LASCO C3 coronagraph, a solar telescope designed to observe the sun's corona by blocking the bright disk. LASCO captures images of the space around the sun, and comets occasionally pass through its field of view. Sarita documented something unusual. In multiple frames, 3I Atlas appeared to display geometric light structures, not the diffuse circular glow you'd expect from a comet's coma. Sharp-edged patterns. In one image, the glow formed what he described as a cross-like plasma geometry, before the object disappeared from the next several frames, then reappeared, then vanished again. We'll explore those geometric patterns in depth later. For now, understand that the October 21st deviation was just the beginning. The numbers were starting to scream something our models couldn't explain.
And in 7 days, 3I Atlas would disappear behind the sun, hidden during the exact window when answers matter most. Brightness in astronomy isn't just about how much light reaches your telescope. It's a diagnostic tool, a way of reading what an object is made of, how active it is, how much surface area is exposed to solar radiation. When a comet approaches the sun, predictable things happen. Ice sublimates, turning directly from solid to gas. That gas drags dust particles off the nucleus, creating the familiar coma and tail.
The coma scatters sunlight, making the comet appear brighter. The closer to the sun, the more heating, the more sublimation, the brighter the display. This relationship is so reliable that astronomers can predict comet brightness months in advance with reasonable accuracy.
3IR Atlas broke that pattern. The Jet Propulsion Laboratory's predictions based on standard models of cometary behavior and the object's known size and trajectory expected an apparent magnitude near 14.8 in late October. Magnitude is a logarithmic scale where lower numbers mean brighter objects. The difference between magnitudes 14 and 15 might not sound like much, but each full magnitude represents about 2.5 times more or less light. So magnitude 15.1, what observers actually measured, means the object was roughly 26% dimmer than expected. That might seem like a minor discrepancy. Comets are unpredictable. Their activity waxes and wanes. Rotation can hide or expose active regions. Dust production varies based on composition. All of this creates uncertainty in brightness predictions. But here's what makes this particular dimming so puzzling. The James Webb Space Telescope confirmed active outgassing. Spectroscopic observations showed carbon dioxide water, vapor, carbon monoxide cyanide, and ionized nickel streaming off the nucleus. The production rates measured by Webb suggested the object was losing approximately 25 kilograms per second during observations in late August. That's not a dormant comet. That's an active system shedding material at rates comparable to many solar system comets. When you have that much outgassing, you create a substantial coma, a cloud of gas and dust surrounding the nucleus. That coma scatters sunlight. The more material in the coma, the more scattering, the brighter the comet appears from Earth. Standard photometric models account for this. You measure the production rate of gas, estimate the dust-to-gas ratio based on spectroscopy, calculate how much sunlight that dust will scatter, and predict the resulting brightness. For 3I Atlas, those calculations suggested magnitude 14.8. Instead, telescopes saw 15.1. The first explanation that comes to mind is composition. Maybe 3I Atlas has an unusually low dust-to-gas ratio. Pure gas doesn't scatter visible light as efficiently as dust particles. If the object is ejecting mostly volatiles with very little particulate matter, the coma would be less reflective than expected, producing a dimmer appearance despite high activity. That's plausible. Interstellar comets might form under different conditions than solar system comets. Different temperatures, different pressures, different chemical environments could produce objects with unusual ratios of ice to dust. But Webb spectroscopic analysis showed dust signatures, silicates, organic compounds, the kind of particulate matter that should scatter light effectively. The spectrum wasn't that of a purely gaseous coma. There was solid material present. So the low dust hypothesis doesn't quite work unless the dust grains are much smaller than typical comet dust. Very small particles, smaller than the wavelength of visible light, scatter less efficiently. They could explain reduced brightness despite confirmed dust presence. That's possible, though. It requires another unusual characteristic stacked onto an already unusual object. The second explanation involves geometry and viewing angle. Comets aren't spherically symmetric. They have jets, localized regions of activity where sublimation is concentrated. If the main active regions on 3I Atlas are pointed away from Earth, we might be seeing primarily the reflected sunlight from the nucleus itself rather than the bright scattered light from the coma's dust. This happens with solar system comets occasionally. A comet can be very active but appear relatively faint from Earth if we're viewing it from an unfavorable angle, except we have confirmation of a visible coma. Hubble images from July showed a distinct teardrop-shaped cocoon of material trailing the nucleus. The anti-tail, observed through August, demonstrated asymmetric outgassing strong enough to create a visible structure pointing toward the sun. If jets were active enough to produce those features, they should be bright enough to show up in integrated brightness measurements. The viewing angle explanation only works if the geometry changed dramatically between the Hubble observations in July and the brightness measurements in October. And there's no obvious reason why that would happen. Then there's the possibility of surface changes. Comets can develop insulating crusts, layers of dust and organic material that reduce sublimation rates as the surface heats. Fresh ice sublimates quickly when first exposed to solar radiation. Over time, the most volatile ices are lost, leaving behind a lag deposit of less volatile material that acts like a blanket slowing heat transfer to subsurface ice. This process makes comets fade as they age. An interstellar comet, having spent potentially billions of years in deep space at temperatures barely above absolute zero, might have all its volatile surface ice locked away under such a crust. As it approaches the sun, that crust heats up but doesn't necessarily lead to proportional increases in activity. The object could be outgassing vigorously from localized fractures or weak spots while most of its surface remains dormant. That scenario fits some of the observations. High activity in specific regions creating the observed mass loss but overall dim appearance, because most of the surface isn't contributing to the coma. It's a reasonable natural explanation, but it creates another question. If the surface is largely inactive, where is all that carbon dioxide coming from? Webb measured substantial carbon dioxide production much higher than the water production rate. Carbon dioxide sublimation requires specific temperature thresholds. It suggests either exposed carbon dioxide ice or subsurface reservoirs connected to the surface through cracks or vents. Either way, you'd expect to see regional brightening around those active areas.
Hotspots that would show up in high-resolution imaging. The high-rise observations from Mars Reconnaissance Orbiter could potentially resolve this. With a pixel scale of about 30 kilometers, they should be able to distinguish between a uniformly dim object and one with bright active regions concentrated in specific areas. But those images remain unreleased. As of October 23rd, NASA cited the government shutdown as a reason for delays. That explanation sits uneasily with many observers. This is arguably the most significant interstellar object to pass through the inner solar system in recorded history, and data is being held back during the most critical observation window. Maybe there's nothing unusual in those images. Maybe HiRISE saw exactly what you'd expect, a fuzzy blob with a tail, and NASA just hasn't gotten around to processing and releasing the files. Or maybe what they saw requires careful analysis, consultation, verification before going public. We don't know.
And that uncertainty creates space for speculation to flourish. There's another angle to consider here, one that sounds almost conspiratorial but emerges from the data itself. What if the object is deliberately minimizing its brightness? That sounds absurd for a natural body. Comets don't have intentions. They respond to solar heating according to the laws of thermodynamics. But if 3I Atlas were artificial, a probe or spacecraft rather than a comet, brightness management would be a basic operational parameter. Think about human spacecraft design. We coat surfaces with specific materials to control thermal properties and minimize reflectivity when necessary. Stealth satellites use low albedo coatings to reduce visibility. If you're sending a probe across interstellar space and you want it to pass through a planetary system unnoticed, or at least unremarkable, you design it to look like natural debris.
But looking natural from spectroscopy, having the right chemical signatures, is easier than matching brightness curves perfectly. You can outgas water and carbon dioxide intentionally mimicking comet activity. Controlling the exact magnitude at which you appear requires either perfect matching of surface properties or deliberate dimming through geometry, orienting reflective surfaces away from observers. I know how this sounds. We're reaching for technological explanations for what could simply be an unusual but natural comet with atypical composition and structure. The brightness paradox alone doesn't prove anything. Comets surprise us regularly. They flare unexpectedly, fade without warning.
split into fragments exhibit jets that defy modeling. 3I Atlas being dimmer than predicted isn't extraordinary by itself, but place it in context. An object that's dimmer than expected despite confirmed high activity. An object showing trajectory deviations from predicted paths. An object with geometric light patterns that might indicate structured plasma fields. An object with composition anomalies like nickel emissions without corresponding iron. An object arriving on a trajectory optimally aligned with the planetary plane and timed to pass multiple planets. Each piece individually is explainable. Together, they form a pattern that's harder to dismiss. The brightness measurements continue through early November as 3I Atlas emerges from behind the Sun. Observatories worldwide will track its magnitude, looking for the expected post-perihelion brightening. Standard comet models predict significant brightness increases after perihelion as fresh material gets exposed and outgassing intensifies from solar heating. If 3I Atlas follows that pattern, brightening to magnitude 12 or 11, as some predictions suggest, it supports natural explanations. The October dimness was just an artifact of viewing geometry or temporary reduction in activity. But if the object remains dimmer than predicted, if it continues operating below expected brightness despite proximity to the Sun and confirmed outgassing, then we have a sustained anomaly that demands explanation. Systematic dimming implies something about the object's structure or behavior that current comet models don't capture. Either our understanding of interstellar comet composition is fundamentally wrong, or 3I Atlas is managing its observational signature in ways natural objects don't. The universe is full of objects we don't fully understand. Interstellar space is vast and ancient, producing conditions we can't easily replicate or study. 3I Atlas being unusual doesn't make it artificial, but unusual in predictable ways following patterns that just happen to align with what you'd design if you wanted to traverse a planetary system efficiently while minimizing detection. That's when unusual starts looking like something else entirely.
Plasma is the fourth state of matter after solid, liquid, and gas. When you heat a gas, enough electrons tear away from atoms, creating a soup of charged particles that behaves very differently from neutral matter. Lightning is plasma. The sun's corona is plasma. The aurora borealis streaming across polar skies is plasma interacting with Earth's magnetic field. It's everywhere in the universe, making up 99% of visible matter. But it's also notoriously difficult to control. Plasma responds to electromagnetic fields, flows along magnetic field lines, forms structures and instabilities that challenge our best physics models. Natural plasmas in cometary environments are chaotic. Solar wind charged particles streaming from the sun at hundreds of kilometers per second interacts with the comet's coma. That interaction creates a bow shock, a boundary where solar wind slows and compresses. Behind the shock, you get complex turbulence, eddies, irregularities. The result is a diffuse, irregular glow. When you image comets in certain wavelengths, you might see asymmetries, brighter regions where outgassing is stronger. But overall, the light distribution is smooth, following the density gradients of gas and dust in the coma. What you don't typically see is geometry. Sharp boundaries, color separation into distinct zones, cross patterns or other regular shapes. The physics doesn't support it. Plasma without strong external organizing forces spreads, diffuses, follows pressure gradients and magnetic field lines that themselves are tangled and irregular around comets. Getting structured geometry requires either very specific conditions or active field management. On October 20th, David Sarita reviewed images from NASA's LASCO C3 coronagraph. These instruments photograph the space around the sun by blocking the solar disk with an occulting disk, revealing the faint corona and any objects passing through the field of view. Comets show up occasionally, usually as fuzzy blobs with tails streaming away from the sun. Sarita found 3I Atlas in multiple frames.
What caught his attention wasn't the object's presence, but its appearance. In one image, the light distribution around 3I Atlas formed what he described as a cross pattern, not a perfect geometric cross like you'd draw on graph paper, but a distinct fourfold symmetry with brighter regions extending in perpendicular directions. Then, in the next several frames, the object disappeared entirely. LASCO takes images at regular intervals, typically every 12 or 30 minutes, depending on the observation program. Objects in the coronagraph's field of view should appear in consecutive frames as they move through space. They might change brightness slightly due to viewing geometry or activity variations, but they don't vanish and reappear unless something dramatic happens. 3I Atlas vanished for multiple frames, then reappeared, then vanished again. The pattern repeated several times across the observation sequence. Sarita documented this and shared the findings, publicly arguing that the disappearances and geometric patterns suggested something unusual about the object's behavior or structure. Skeptics immediately offered alternative explanations. LASCO images are challenging to interpret. The instrument wasn't designed for deep space observations. It's optimized for solar corona studies, which means its sensitivity and calibration are tuned for specific brightness ranges and wavelengths. Faint objects near the detection limit can appear and disappear due to image processing artifacts, cosmic ray hits on the detector, or simple signal-to-noise fluctuations. If 3I Atlas was at the edge of LASCO's detection threshold, frame-to-frame variations in background noise could make it visible in some images and invisible in others. The cross pattern could be a diffraction artifact. Coronagraphs use complex optical systems with multiple occulting disks and baffles to block sunlight. Bright point sources sometimes create cross-shaped diffraction spikes due to the edges of these optical elements. Stars in LASCO images often show this pattern. If 3I Atlas had a bright central region, a concentrated nucleus, or a particularly reflective spot, it could theoretically produce similar diffraction effects. But Earth exists. The group that documented the trajectory anomalies did independent analysis. They weren't looking at LASCO images. They were processing their own observations from ground-based facilities using standard astronomical CCD cameras attached to moderate aperture telescopes. They applied single-image enhancement, adjusting contrast and brightness to bring out faint details, but they didn't stack multiple exposures or use heavy processing that might create artifacts. Their images showed color separation in the coma. Green outer regions, blue central areas, pink zones distributed around the nucleus. To verify this wasn't an artifact, they imaged reference stars in the same field of view. Spica, one of the brightest stars visible from Earth, appeared as a tight circular point spread function with normal color balance. Comet C 2025 R2 Swan. Another active comet visible in the same region of sky showed a typical cometary appearance with a diffuse circular coma and faint tail. No geometric patterns, no unusual color separation beyond the slight green tint common in cometary comas from diatomic carbon emission. 3IR Atlas looked different. The color zones they measured correspond to known emission lines: green from ionized cyanogen, blue from hydrogen plasma, pink likely from a mix of ionized carbon and other species. These aren't unexpected chemicals. The KEK Observatory confirmed cyanogen presence back in August. Hydrogen emission is standard for comets. What's unusual is the spatial distribution. Normally, these emission regions overlap. You don't get clean separation because the gases mix as they expand from the nucleus. Turbulence, solar wind interaction, and thermal diffusion blur any initial structure within seconds to minutes after material leaves the surface. Maintaining distinct color zones requires something preventing mixing. In laboratory plasmas, that something is usually a magnetic field. Charged particles spiral along field lines confined to specific regions, depending on the field geometry. If you arrange magnetic fields carefully, you can create structured plasmas with well-defined boundaries between regions of different temperature or composition. We do this in fusion reactors. We do it in plasma thrusters for spacecraft. It requires active field coils or permanent magnets with specific configurations. Natural magnetic fields around comets are weak and irregular. Comets don't have internal dynamos like planets.
They're not massive enough or electrically conductive enough to generate strong, self-sustained magnetic fields. They do carry embedded magnetic fields frozen into the material from their formation environment. But these fields are typically chaotic with no large-scale organization. The solar wind brings its own magnetic field, but that's equally disorganized at the small scales relevant to comet comas. Could 3I Atlas have an unusually strong or well-organized internal magnetic field? It's not impossible. If the object formed in a region with strong ambient fields, perhaps near a massive star or in a molecular cloud with aligned magnetic fields, it might have retained some of that structure. Certain minerals like magnetite can preserve magnetic fields over geological timescales. If 3I Atlas has a high concentration of magnetic minerals and they're aligned, you could theoretically get a weak but organized field. But here's the problem with that explanation.
The field would need to be strong enough to organize plasma over distances of hundreds to thousands of kilometers. The scales involved aren't the nucleus itself, which might be 5 to 10 kilometers across. They're the coma, the extended cloud of gas that can reach tens of thousands of kilometers in size for active comets. Creating structured plasma at those scales requires field strengths that far exceed what remnant magnetization in rocks can provide. You'd need active generation current loops, moving charged particles creating magnetic fields through electromagnetic induction. The alternative is that what we're seeing isn't plasma structure at all, it's an optical effect. Selective scattering of sunlight by particles with specific properties distributed in patterns around the object. Certain dust grain compositions preferentially scatter light at particular wavelengths. If 3I Atlas is ejecting different types of dust from different regions of its surface, and those dust types separate spatially as they move away from the nucleus based on size and composition, you could create zones of different color. This happens to some degree in all comets. Heavier particles follow slightly different trajectories than lighter particles. But getting the clean separation observed by Earth exists would require the ejection processes to be extremely organized. Each type of material would need to come from distinct surface regions and maintain that separation as the coma expands. It's difficult but not physically impossible. Some comets show jets with distinct colors when imaged in narrow band filters that isolate specific emission lines. What bothers careful observers is the combination. Color separation plus geometric patterns, plus the disappearing act in LASCO images, plus the trajectory anomalies, plus the brightness paradox. Each piece has potential natural explanations that stretch but don't break physics. All of them together start to feel less like coincidence and more like a system with behaviors we're not equipped to interpret. The cross pattern in particular bothers physicists familiar with plasma confinement. Fourfold symmetry is common in engineered magnetic traps where coils are arranged in quadrupole configurations. Nature rarely produces such clean symmetry without very specific forcing. You see it in crystals where atomic lattices dictate structure. You see it in some planetary magnetospheres where geometric effects from rotation and solar wind interaction create organized patterns. But in a cometary coma far from any rotating body with weak or non-existent internal magnetic fields, getting a cross pattern is hard to justify with standard physics. We'll know more by December. By then, the object will be far enough from the sun that imaging won't be fighting solar glare. The geometry will be favorable for Northern Hemisphere observatories. High-resolution photometry and spectroscopy will either confirm the plasma structures are real and persistent, or show they were observational artifacts specific to difficult viewing conditions in October. Either answer is important. If they're artifacts, we learn about the limitations of our detection methods and the care needed when interpreting faint object images. If they're real, we face something that challenges our understanding of how comets work, or forces us to seriously consider that 3I Atlas might not be a comet at all. Comet tails are one of the most recognizable features in astronomy. They point away from the sun, always, stretched by solar wind and radiation pressure into long streamers that can extend millions of kilometers into space. The physics is straightforward. Sunlight carries momentum. When photons hit dust, particles ejected from a comet, they transfer that momentum, pushing the particles away from the sun. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second, does the same thing to ionized gas. Both effects work in the same direction, away from the source of radiation and wind, creating the classic comet tail. Sometimes you see two tails. A dust tail curved slightly because dust particles are massive enough that their orbital motion matters, and an ion tail straight and often bluish, made of ionized gas that responds primarily to the solar wind's magnetic field. Both point away from the sun. This is so fundamental to cometary behavior that it's one of the first things you learn in introductory astronomy. Tails point away. Always. Except when they don't. Anti-tails, properly called anthelion tails or sunward spikes, are rare but documented features where material appears to stream toward the sun rather than away from it. The name is slightly misleading because it's usually an optical illusion. Perspective effects when viewing the comet from certain angles can make part of the tail appear to project forward. Imagine looking at a curved structure nearly edge-on. The parts of the curve that extend toward you look like they're pointing in the opposite direction from the parts extending away. Anthelion tails result from viewing geometry, not actual sunward motion of material. 3I Atlas showed something different. The Hubble Space Telescope imaged it on July 21st, capturing a high-resolution view of the coma and surrounding material. The image revealed a pronounced sunward spike material extending from the nucleus in the direction of the sun. Not a subtle perspective effect. A clear, distinct structure, with about 2:1 elongation in the projected view. But when Avi Loeb and Eric Kito corrected for viewing angle, they calculated the three-dimensional elongation was approximately 10:1. That's a jet, not an optical illusion. The physics of creating a sunward jet is counterintuitive. You're fighting radiation pressure and solar wind. Both want to push material away from the sun. To create a jet aimed sunward, you need a mechanism that overcomes those forces. The explanation Loeb and Kito proposed in their September paper involves the specifics of how ice sublimation works. When carbon dioxide ice on the comet's surface absorbs solar radiation, it sublimates, turning directly from solid to gas. That gas expands rapidly, carrying with it water ice fragments that were embedded in or resting on the carbon dioxide ice. Those ice particles, now separated from the surface, scatter sunlight efficiently, creating the visible glow we see as a coma, but they also sublimate. Water ice at the temperatures relevant here, a few hundred Kelvin, doesn't last long. The ice particles themselves turn to gas over timescales of minutes to hours, depending on their size. If the sublimation process ejects ice particles with significant velocity, and those particles start sublimating immediately, they create a stream of material that moves away from the nucleus but continually loses mass. The trick is timing. At distances of 3 to 4 astronomical units from the sun, water ice sublimation produces a peak in the scattering cross-section. There's enough solar heating to sublimate the particles quickly, but not so much that they vanish instantly. The balance creates a region where the density of light-scattering ice particles is maximum. If that maximum density region happens to be offset toward the sun from the nucleus, you get an anti-tail. The particles are moving outward in all directions from the comet, but the ones moving sunward last longer before fully sublimating compared to the ones moving away from the sun. That asymmetry in particle lifetime creates an apparent asymmetry in the brightness distribution. It's still an optical effect in some sense, not truly sunward motion, but it's based on real physics of how sublimation rates vary with heliocentric distance. That's the natural explanation for what Hubble saw in July. It works mathematically. The model Loeb and Quito published fits the observed elongation ratios and brightness distributions, but it also predicts something specific. As 3I Atlas continues approaching the Sun, moving from 4 astronomical units inward to 2, then to perihelion at 1.356, the sublimation rates should change. Water ice particles ejected at closer distances sublimate faster.
The peak scattering region shifts. Eventually, the anti-tail structure should disappear, replaced by more symmetric outgassing, and then potentially by a traditional tail, as refractory dust that doesn't sublimate quickly begins to dominate the coma. In September, new images from the Nordic Optical Telescope in the Canary Islands confirmed the prediction. The anti-tail had diminished. In its place, a faint tail extended away from the sun, the normal configuration you'd expect from a comet. David Jewett and Jane Liu published the analysis in mid-October, documenting the transition with photometric measurements showing the change in mass flow geometry. This should be satisfying. A prediction made, tested, confirmed. Natural comet behavior explained by well-understood physics. The anti-tail wasn't evidence of propulsion or technological control. It was sublimation physics, playing out exactly as theory suggested. Case closed.
But here's where Adam Hibbard, one of Loeb's colleagues at Harvard, raised an uncomfortable question. If you were operating a spacecraft and wanted to slow down as you approached a star system, you'd fire your engines in the direction of travel-creating thrust that opposes your velocity. That's called a retrograde burn in spaceflight terminology. The exhaust would stream ahead of the spacecraft, creating a visible plume pointing toward your destination. From an external observer's perspective, it would look exactly like an anti-tail, material extending toward the sun opposite the expected direction. Then, as you complete your braking maneuver and need to adjust your trajectory for planetary encounters, you might reverse thrust. Orientation fire the engines in the opposite direction to provide acceleration or make course corrections. That exhaust would stream behind the spacecraft, creating a traditional tail-like structure. Again, from an observer's perspective, it would appear identical to what 3I Atlas just did. Anti-tail in July and August. Transition period in September. Normal tail by October. The timing fits disturbingly well. If 3I Atlas were a spacecraft executing a deceleration burn followed by perihelion, maneuvering the sequence of anti-tail-to-tail transition would occur over exactly the timescale observed. The total mass ejected about 2 million tons, according to integrated production rate measurements, represents roughly 0.005 of the object's total mass. That's a surface layer about 4 centimeters thick if spread evenly across a 5-kilometer diameter sphere. For a natural comet, 4 centimeters of ablation is trivial. Comets regularly lose meters of surface material during perihelion passages. The amount lost tells us almost nothing about what's underneath.
For a spacecraft with a protective coating designed to mimic comet activity while shielding internal systems from solar radiation, 4 centimeters is exactly what you'd expect. Enough material to create convincing spectroscopic signatures and visible activity, but not so much that you risk exposing underlying structure. Loeb has been careful to acknowledge that the natural explanation for the jet flip is perfectly adequate. The Quito Loeb model doesn't require anything exotic.
Its standard thermodynamics and radiative transfer, the sublimation rates, particle sizes, and scattering properties all fit within normal ranges for cometary materials. If you showed these observations to most planetary scientists without mentioning 3I Atlas's other anomalies, they'd agree it's consistent with a comet transitioning from distant cold activity, dominated by carbon dioxide, to closer, warmer activity, where refractory dust becomes important. The problem is those other anomalies don't go away. The trajectory deviations, the brightness paradox, the geometric plasma patterns, the composition oddities like nickel without iron, extreme negative polarization, the orbital alignment with the ecliptic, and the timing that brings it close to multiple planets. Each piece has natural explanations, but each natural explanation requires different special conditions. Unusual composition to explain the nickel. Unusual dust properties to explain the polarization, unusual magnetic fields to explain the plasma geometry, unusual viewing geometry to explain the brightness. At some point, invoking multiple independent unusual conditions becomes less parsimonious than considering a single explanation that accounts for everything. If 3I Atlas is technological a probe or spacecraft rather than a natural comet, then all the anomalies resolve into expected behavior for an engineered system operating in an environment it wasn't originally designed for. The composition reflects manufacturing processes rather than natural formation. The trajectory reflects deliberate navigation rather than gravitational freefall. The brightness management reflects operational priorities like power generation or thermal control rather than simple thermodynamic response to solar heating. The jet orientations reflect propulsion system operation rather than asymmetric sublimation. That's the hypothesis Adam Hibbard explored in his analysis. Not claiming it's definitely artificial, but pointing out that the artificial hypothesis eliminates the need for multiple stacked coincidences. Occam's razor, the principle that simpler explanations are preferred, usually favors natural interpretations. A rock is more likely than a spacecraft, but Occam's razor also says you should minimize the number of independent assumptions. One exotic assumption that the object is technological versus 7 or 8 independent unusual natural conditions changes the calculation. The post-perihelion observations will test this directly. If 3I Atlas is natural, it should continue showing comet-like evolution. The tail should brighten as fresh material gets exposed by solar heating. Spectroscopic signatures should remain consistent with icy body composition. Activity should gradually decline as the object moves away from the sun and temperatures drop. All of this is predictable from thermodynamics. If it's artificial and the anti-tail really was a braking burn, then the post-perihelion behavior might look different. Activity could drop more sharply than expected if the propulsion system shuts down after completing its maneuvers. Spectroscopic signatures might shift if the surface coating exhausts and underlying materials become visible. The brightness might stabilize at levels inconsistent with continued sublimation of ice. Any of these would be difficult to explain with natural comet models. There's also the possibility of secondary deployments. If the object is a mothership, as Loeb speculated, perihelion is when you'd release smaller probes, mini spacecraft, designed to intercept planets, asteroids, or other targets of interest. Those deployments would show up in photometry as sudden changes in brightness, or in astrometry as multiple distinct light sources where there was previously one. High-cadence monitoring through November and December specifically looks for these signatures. The jet flip itself doesn't prove anything. It's consistent with natural comet behavior, but it's also consistent with spacecraft propulsion. The fact that both explanations work means we need additional data to distinguish them. The critical observations are coming in the next few weeks. Does the tail behavior continue following natural sublimation models? Does the object's trajectory remain purely gravitational or show continued deviations? Do we see any evidence of fragments or secondary objects separating from the main body? Loeb has stated publicly that if 3I Atlas behaves naturally through the perihelion passage and subsequent observations, he'll downgrade its ranking on his scale to 2, meaning unusual but probably natural. The anomalies would remain interesting, worthy of study, but not indicative of technology. However, if the post-perihelion data shows anything inconsistent with natural evolution, if the object continues defying standard comet models in systematic ways, then the technological hypothesis becomes harder to dismiss. We're watching a test unfold in real time. Nature has given us an interstellar visitor with enough oddities to raise questions, but not enough clear evidence to force conclusions. The jet flip, the transition from anti-tail to tail, is one piece of that puzzle. Understood in isolation, it's unremarkable. Understood in context with everything else, 3I Atlas has shown us it becomes one more data point in a pattern that refuses to resolve into comfortable familiarity. There's a specific term in orbital mechanics that most people never encounter unless they study spaceflight or planetary science. Solar conjunction. It sounds technical, almost bureaucratic, but what it describes is remarkably simple. It's when an object in space passes directly behind the sun from Earth's perspective, becoming completely invisible to our telescopes, because the sun's overwhelming brightness drowns out everything near it. For 3I Atlas, solar conjunction happened on October 21, 2025, the exact same day those trajectory deviations started appearing in independent tracking data. Think about the geometry for a moment. Earth, Sun, 3I Atlas all lined up in a straight row with the sun in the middle. From our vantage point, the object vanished into the solar glare, not behind the physical disk of the sun that would require precise alignment down to arc seconds, but close enough that the sun's corona, that super-hot outer atmosphere extending millions of kilometers into space, creates a blinding background that makes observation impossible. Even our most powerful coronagraphs instruments, specifically designed to block the sun's disk and study the area around it, struggle to pick out faint comets when they're this close to solar alignment. This alignment doesn't last forever. Objects move. Earth orbits. The geometry shifts. But for 3I Atlas, the timing created something unusual. Solar conjunction on October 21st meant the object entered the zone of unobservability 8 days before perihelion, 8 days before its closest approach to the sun on October 29th at 11:36 Universal Time. Those 8 days represent the period when the object would be accelerating to its maximum velocity, experiencing peak solar radiation. And if it were anything other than a natural comet executing the most critical phase of its mission profile. Let's talk about what happens at perihelion from an engineering perspective. If you're sending a probe to another star system and you want it to perform maneuvers within that system, you don't do it randomly. You follow the principles of orbital mechanics that have governed spaceflight since we started leaving Earth's atmosphere. The Oberth effect, formulated in the 1920s, tells us that the most efficient time to change a spacecraft's trajectory is when it's moving at its highest velocity. The math is straightforward. Kinetic energy equals 1/2 mass times velocity squared. That squared term matters enormously. If you're moving at 10 kilometers per second and you add 1 kilometer per second of thrust, the energy change is much smaller than if you're moving at 50 kilometers per second and add that same 1 kilometer per second. The faster you're already going, the more energetic punch you get from each unit of thrust. For 3I Atlas, maximum velocity occurs at perihelion. At that point, falling toward the sun's gravity, while the object will be traveling at approximately 68 kilometers per second relative to the sun. If you wanted to release probes that could intercept planets in the inner solar system, perihelion is when you do it. A small velocity change at that moment, maybe 10 or 15 kilometers per second in the right direction, could redirect a mini probe toward Earth, Mars, or Venus with relatively modest fuel expenditure. Wait until you're farther out, moving slower, and the same maneuver costs exponentially more energy. This isn't speculation about alien engineering. This is how human spacecraft work. When we send probes to the outer solar system, we use gravity assists to gain speed, and we time our engine burns for moments of peak velocity.
The Voyager mission's New Horizons. Every deep space probe follows these principles because physics doesn't care about your intentions. The math works the same whether you're NASA or something that evolved under a different star. Now overlay that engineering reality onto 3I Atlas's timeline. October 21st, solar conjunction begins. October 29th, perihelion passage at 1356 astronomical units. During those 8 days, Earth-based telescopes see nothing. Mars, orbiters might catch glimpses if they're looking at the right moment, but the Sun's position relative to Mars means even those observations are limited. The European Space Agency's JUICE spacecraft, currently between Earth and Jupiter on its way to the outer system, will attempt observations in early November. But during the critical perihelion window, 3I Atlas operates in essentially complete darkness from our perspective. The distance, 1.356 astronomical units, places it about 203 million kilometers from the Sun. For context, Earth orbits at 1 astronomical unit, Mars at about 1.5. Perihelion for 3I Atlas puts it closer to the Sun than Mars's orbit, but farther than Earth's. It's a position that offers tremendous solar energy for power generation if you were a technological system, but not so close that temperatures would vaporize metals or destroy electronics with proper shielding. A habitat designed to operate in interstellar space, shielded against cosmic radiation and near absolute zero temperatures, would find this distance almost balmy by comparison. The solar radiation flux at that distance would deliver approximately 33 gigawatts of power to the object's surface, assuming Loeb's minimum diameter estimate of 5 kilometers. 33 gigawatts, that's roughly the output of 30 large nuclear power plants. If even a fraction of that could be captured and converted to useful energy, you'd have more than enough to run any conceivable propulsion system, communications array, or manufacturing process. Again, this isn't implying 3I Atlas is technological. It's pointing out that, if it were perihelion, would be the ideal moment to do whatever it came here to do, and solar conjunction ensures we won't be watching when it happens. The orbital parameters tell another story that's easy to miss if you're not looking for it. 3I Atlas has an eccentricity of 6.137. Eccentricity is a number that describes how elliptical or hyperbolic an orbit is. A circle has eccentricity 0. Earth's slightly elliptical orbit has eccentricity 0.017. Anything above 1.0 is a hyperbolic trajectory, meaning the object isn't bound to the Sun and will eventually escape. 6.137 is extraordinarily hyperbolic. The trajectory is almost a straight line barely curved by the Sun's gravity. This object is passing through our solar system at such high speed that even our star's immense gravitational pull only bends its path slightly. That extreme eccentricity means something else too. Time spent in the inner solar system is minimal. 3I Atlas didn't spend months slowly falling toward the Sun like comets from the Oort cloud. It came screaming in from interstellar space at 58 kilometers per second and will leave at roughly the same speed. The entire passage from discovery in early July to departure from the inner system by late December spans about 6 months. Compare that to long-period comets that can spend years in the inner system, or short-period comets that return every few years or decades. This is a flyby in the truest sense, a brief interaction with the Sun before continuing into the galactic disk. But here's where it gets interesting. The trajectory isn't just hyperbolic, it's aligned. The orbital plane of 3I Atlas matches the ecliptic, the plane defined by Earth's orbit around the Sun, to within 5 degrees. Most objects coming from interstellar space would approach from random angles. The galaxy doesn't care about our ecliptic. Comets from the Oort cloud gravitationally bound to the Sun but barely come from every direction imaginable. Retrograde orbits.
Prograde orbits, high inclinations, low inclinations. There's no preferred direction. 3i Atlas is different. Its inclination of 175 degrees means it's moving retrograde opposite to the direction planets orbit, but the plane itself is nearly aligned with ours. Loeb calculated the probability of that alignment occurring by chance at roughly 0.2%. That's not impossible. 2 in 1,000. But it's uncommon enough to raise eyebrows. A trajectory aligned with the planetary plane makes interception easier. If you're trying to release probes that will encounter multiple planets starting from a trajectory already in their orbital plane, saves enormous amounts of fuel compared to making major plane changes, which are among the most expensive maneuvers in orbital mechanics. Add the timing. The arrival time of 3i Atlas brings it within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, and Jupiter on March 16, 2026. The probability of a random interstellar object happening to pass close to 3 major planets during its flyby is vanishingly small. Loeb and his colleagues calculated it at roughly 0.005%, 5 in 100,000. These aren't impossible odds, but they're starting to accumulate in ways that make pattern recognition circuits in our brains light up. Is it coincidence that perihelion happens during solar conjunction? From a physics standpoint, there's no connection.
Solar conjunction is about Earth's position relative to the object's trajectory. Perihelion is about the object's closest approach to the Sun. They're independent parameters. The fact that they occur 8 days apart, creating a window where the object is both at peak velocity and hidden from observation, is just how the orbital geometry worked out. But if you were planning an interstellar mission and could choose your approach vector, you'd absolutely design it this way. Hide the most critical phase behind the brightest object in the system. The question becomes testable on November 3rd when 3i Atlas emerges from behind the Sun. We'll have clear lines of sight again. Multiple observatories will track its position, measure its brightness, analyze its spectrum. If the trajectory deviations observed in late October were real and sustained, they'll show up in the post-perihelion dates. The offset should be larger, the divergence from purely gravitational motion more obvious.
If those deviations were measurement errors or temporary outgassing anomalies, the object will return to its predicted path, and all the speculation evaporates. But there's a third possibility that keeps astronomers up at night. What if the trajectory matches predictions perfectly after perihelion, but the spectroscopic signature changes? What if the composition looks different? The activity level drops or spikes in unexpected ways. The polarization shifts. Loeb has said publicly that if 3i Atlas survives perihelion intact and continues showing natural comet characteristics, he'll downgrade it to rank 2 on his scale. Still anomalous, still interesting, but probably natural. However, if post-perihelion observations reveal anything unusual changes that suggest the object is no longer the same system we were tracking before it disappeared, then rank 4 might not be high enough. The mass estimates suggest something durable, at least 33 billion tons based on the lack of non-gravitational acceleration despite visible outgassing. That mass combined with a diameter around 5 kilometers implies an object that's either incredibly dense or has significant structural integrity. Most comets are loosely bound ice and rock porous structures that sublimate and shed material easily. If 3i Atlas is that massive and hasn't shown trajectory changes from outgassing, either the outgassing is perfectly symmetric, which seems unlikely given the observed anti-tail that existed in July and August, or the object's mass is large enough that even vigorous outgassing produces negligible recoil. Either way, it's built to last. Perihelion at 1.356 astronomical units isn't going to destroy it. The question is what it does during those hidden days. Does it break apart naturally, creating fragments that will become visible as they separate over the following weeks? Does it release material intentionally smaller objects that begin their own trajectories towards specific targets? Or does it simply continue on its hyperbolic path unchanged, except for the expected brightening and possible increase in outgassing from solar heating? We're about to find out. By the time November arrives, 3I Atlas will have completed its close approach, absorbed 33 gigawatts of solar radiation over several days, and if it's anything other than a comet, executed whatever maneuvers or deployments were planned for this moment. The post-perihelion observations will either confirm its natural, revealing nothing unusual despite the earlier anomalies, or they'll show something that forces us to take the technological hypothesis seriously. There's no middle ground anymore. The data either supports natural explanations or it doesn't. And somewhere between Earth and that hidden point behind the sun during 8 days, when no telescope can watch, 3I Atlas does what it came here to do. The universe waits patiently while we close our eyes. Elements tell stories, the specific atoms present in an object, their ratios, their isotopic signatures. These reveal where something formed under what conditions, through what processes. In August 2025, the Keike Observatory in Japan pointed their spectrograph at 3I Atlas and measured the light coming from its coma. Spectroscopy works by splitting light into its component wavelengths. Each chemical element emits or absorbs light at characteristic frequencies, creating a unique fingerprint we can read from millions of kilometers away. The Keike data showed something unusual. Strong nickel emission lines, ionized nickel glowing as it absorbed solar ultraviolet radiation and re-emitted visible light. That alone isn't extraordinary. Metals exist in comets. They're rare compared to ices and silicates, but they're their remnants from the stellar materials that formed the comet's parent system. What was extraordinary was what wasn't there. Iron. Nickel and iron are sister elements. They're born together in stellar nuclear fusion. When massive stars forge elements heavier than helium in their cores, they produce iron and nickel in relatively fixed ratios. When those stars die in supernovae, they scatter those elements into space, where they eventually condense into planets, asteroids, comets. Every rocky body in our solar system shows this relationship. Meteorites carry iron and nickel together. Asteroids sampled by spacecraft missions show coupled abundances. Even comets, when they have detectable metal content, display iron alongside nickel. The cosmic abundance ratio of iron to nickel is about 18:1. You find 18 iron atoms for every nickel atom, give or take, throughout the universe. That's what stellar physics predicts. That's what observations confirm. 3I Atlas showed prominent nickel emission without corresponding iron lines. The Keike team checked their calibrations. They compared their results to reference spectra from known comets. They looked at multiple observation nights to ensure this wasn't a transient artifact. The pattern held. High nickel, essentially no detectable iron. How do you explain that natural processes do allow some chemical fractionation? Under extreme conditions, elements can separate based on subtle differences in their chemical behavior, but the conditions required are unusual. One possibility, 3I Atlas formed in an environment where iron preferentially bound into compounds that don't emit visible light. Perhaps iron-rich minerals in the nucleus don't sublimate at the temperatures 3I Atlas experienced in August. The iron is there, but locked in refractory materials, while nickel volatilizes more easily, creating emission we can see. This works in principle. Different minerals have different vapor pressures. If the object's formation environment created unusual mineralogy, you might get selective volatilization that produces nickel-rich gas without iron, but it requires very specific mineralogical conditions. Conditions we don't commonly observe in solar system comets because the processes that create them are rare. There's another context where you find high nickel without iron: industrial alloys. Stainless steel uses nickel to enhance corrosion resistance and mechanical properties. Superalloys for jet engines contain high nickel concentrations because nickel maintains strength at extreme temperatures. Corrosion-resistant materials deliberately concentrate nickel while minimizing iron. We do this on Earth because of nickel's useful properties. The resulting alloys have nickel-to-iron ratios that can be inverted from natural cosmic abundances, more nickel than iron, sometimes dramatically so. Finding that signature in a comet is like finding refined aluminum in a meteorite. Not impossible if some exotic natural process creates extreme chemical fractionation, but so rare that alarm bells start ringing. I want to be clear, one spectroscopic anomaly doesn't prove anything. Interstellar space is vast. Formation conditions vary wildly between stellar systems. 3I Atlas could have originated in a molecular cloud with unusual chemistry or been processed by radiation and thermal cycling over billions of years in ways that altered its composition. The nickel-iron ratio alone is unusual but explainable. What makes it significant is the pattern it creates with other anomalies. In September, the Very Large Telescope in Chile observed 3I Atlas and measured its polarization. Polarization describes how light waves are oriented after scattering off particles. When unpolarized sunlight hits dust grains, it becomes partially polarized. The degree and direction of polarization depend on the size, shape, and composition of those particles. Most comets show positive polarization, light waves aligned perpendicular to the scattering plane. This is standard for dust particles in the size range typical of cometary debris micrometers to millimeters in diameter. 3I Atlas showed extreme negative polarization. Light waves align parallel to the scattering plane. The Very Large Telescope team noted the probability of such extreme polarization occurring naturally in a comet is below 1%. Negative polarization can happen with very specific particle size distributions. Laboratory studies show certain types of dust produced under controlled conditions can create this signature. But finding it in an active comet where particle sizes vary widely and composition is mixed is extraordinarily rare. It suggests either the dust from 3A Atlas is remarkably uniform in size, all particles clustered around some optimal diameter for producing negative polarization, or the composition includes materials with unusual optical properties not commonly found in solar system comets. Or third option, the polarization isn't coming from scattered sunlight at all. It's emission from some other process that happens to produce polarized light. Synchrotron radiation from charged particles spiraling in magnetic fields produces highly polarized emission. So do certain plasma processes. If what we're seeing isn't reflected sunlight, but rather emission from a magnetized plasma surrounding the object, the polarization signature would look very different from typical comet dust scattering. This connects back to the geometric light patterns we discussed earlier. Structured plasma fields producing organized emission with specific polarization characteristics would explain both the geometry and the polarization measurements. But it requires magnetic fields strong enough to organize plasma over scales of hundreds to thousands of kilometers. Natural comets don't have that kind of field strength. Then there's the density question. Richard Cookite, Peter Verres, and Avi Loeb analyzed over 4,000 positional measurements from 227 observatories worldwide spanning from mid-May through late September. They found no detectable deviation from purely gravitational motion. For an active comet, losing 25 kilograms per second, that's strange. Outgassing creates recoil forces. Those forces push the nucleus off its gravitational trajectory by small but measurable amounts. We see this in solar system comets routinely. The magnitude depends on the comet's mass and the strength of outgassing. Small active comets show large deviations. Large comets show smaller but still detectable deviations. 3I Atlas showed nothing. The residuals in right ascension and declination were consistent with zero. That means either the outgassing is perfectly symmetric forces canceling out, or the object's mass is so large that the recoil is below detection threshold. Perfect symmetry is inconsistent with the observed anti-tail and geometric plasma patterns, which indicate asymmetry. So the object must be extremely massive. Working backward from the detection limits, the analysis concluded 3I Atlas must be at least 33 billion tons. That's about 1,000 times more massive than 2I Borisov, despite being only a few times larger in diameter. The implied density is much higher than typical comets. Comets are loosely bound rubble piles with lots of empty space porosities often exceeding 50%. Densities typically range from 0.3 to 0.6 grams per cubic centimeter, less dense than solid water ice. To pack 33 billion tons into a 5-kilometer diameter object requires density around 2 grams per cubic centimeter or higher. That's not porous ice and rock, that's consolidated material, solid structure with minimal void space. Either the object is primarily dense rock rather than ice, or it has internal architecture that's not porous like typical comets. High density, unusual composition, extreme polarization, structured plasma trajectory, alignment, planetary encounter timing. Each piece requires its own special explanation. Taken together, they start suggesting something about this object that doesn't fit comfortry frameworks. If 3I Atlas formed naturally, but under extraordinarily unusual conditions, perhaps ejected from a stellar system very different from ours, processed through interstellar space in ways we don't understand, arriving by chance during our brief technological window, then it represents an extreme outlier in the distribution of interstellar objects. If it's artificial, then the composition reflects deliberate material selection. Nickel alloys for structural strength and corrosion resistance. High density from manufactured construction. Polarization from surface coatings with specific optical properties. Plasma organization from active electromagnetic field management. One hypothesis requires many low-probability natural conditions. The other requires one extraordinary artificial origin. That's the essential tension we face. And composition measurements continuing through November will either reinforce the natural interpretation or make the artificial hypothesis unavoidable. Space is vast, three-dimensional, infinite in its possibilities for how objects might move through it. When something arrives from interstellar space, it could come from any direction, up, down, sideways, relative to our solar system's orientation, high inclinations cutting across the planetary orbits at steep angles, retrograde motion opposite the direction our planets travel, prograde motion aligned with their direction but tilted at random angles. The galaxy doesn't care about our ecliptic plane. There's no preferred orientation. Objects ejected from other stellar systems tumble through the galactic disk with trajectories determined by their ejection dynamics. Gravitational kicks from giant planets, stellar encounters, supernova shocks. By the time they cross the vast distances between stars and happen to pass near our sun, their approach vectors are essentially random samples from all possible angles. Oumuamua arrived at 122 degrees inclination, highly tilted relative to our planetary plane. 2I Borisov came in at 44 degrees. Both were inclined enough that accessing planets would require significant velocity changes, expensive plane change maneuvers that cost enormous amounts of fuel. 3I Atlas arrived at 175 degrees inclination. That number needs explanation. Inclination is measured from 0 to 180 degrees. 0 means you're moving in the same plane as Earth's orbit in the same direction. 90 degrees means you're perpendicular to that plane. 180 degrees means you're in the plane but moving opposite to Earth's direction, retrograde. 175 degrees is almost exactly retrograde motion within the ecliptic plane. The object is moving through the same orbital plane as our planets, just backward. It's traveling opposite to their direction, but it's aligned with their flat disk structure. Only 5 degrees of tilt separates 3I Atlas from perfect alignment. In the universe of possible trajectories, that's remarkably close. Loeb calculated the probability at about 2%. 2 in 100 interstellar objects would arrive with that degree of alignment by pure chance. Not impossible, but uncommon. Why does alignment matter? Orbital mechanics. Changing the plane of your trajectory is one of the most expensive maneuvers you can make. It requires velocity changes perpendicular to your motion, and those changes don't benefit from gravitational assists. The way speed increases do when you're already moving in the right plane. If you're designing a mission to explore a planetary system and you have limited fuel, you choose a trajectory that minimizes plane changes. You align with the system's primary plane so that reaching different planets requires only speed adjustments and timing, not massive reorientations. Human spacecraft do this routinely. When we plan missions to outer planets, we launch when Earth's orbital position gives us optimal alignment with the target. We use gravity assists from inner planets to adjust our trajectory without burning fuel. Every degree of inclination matters because every degree costs velocity you might need elsewhere. 3i Atlas. Approaching within 5 degrees of the ecliptic gives it optimal access to every planet in the inner solar system with minimal fuel expenditure for plane changes. Now add the timing. The object didn't just pass through our planetary system at random. It arrived when Mars was positioned for close approach on October 3rd, when Venus would be accessible on November 3rd, when Jupiter would be within reach on March 16, 2026. Close approaches to multiple planets during a single hyperbolic pass are rare. Most interstellar visitors either miss everything or perhaps pass near one planet by luck of geometry. The probability of timing your arrival to encounter 3 major planets. Loeb and colleagues calculated it at roughly 0.005%, 5 in 100,000. Let that accumulate. 2% chance of ecliptic alignment times 0.05% chance of multi-planet encounter timing. You're at 0.01%, 1 in a million already, and we're only considering 2 parameters, but there's more. The approach velocity, 58 kilometers per second. Hyperbolic excess velocity places 3i Atlas among the fastest interstellar objects ever detected. That high velocity combined with large mass 33 billion tons minimum creates extraordinary kinetic energy. Most massive objects are gravitationally bound to their parent stars. Getting something that big moving that fast requires extreme ejection events. Not impossible stellar collisions, close encounters with massive black holes, supernova kicks can do it. But such events are uncommon. The probability of detecting a massive high-velocity interstellar object during the few decades when humanity has the technology to identify them, well below 1%. 3 low-probability conditions all present in the same object. Alignment timing, mass-velocity combination. Each explainable independently. Together they start creating what statisticians call a compound improbability. But wait. There's another correlation that emerged months after 3i Atlas was discovered, one that connects this object to humanity's most famous potential extraterrestrial signal. August 15, 1977, the Big Ear radio telescope at Ohio State University detected a 72-second signal at 14 to 20 megahertz. That frequency sits right in the middle of the hydrogen line, the radio emission from neutral hydrogen atoms that pervades the galaxy. It's a natural choice for interstellar communication because hydrogen is the most abundant element in the universe. Any technological civilization would know that frequency well. The signal was so much stronger than background noise that astronomer Jerry Amon, reviewing the computer printout days later, circled the alphanumeric sequence and wrote in the margin, "Wow." That annotation gave it its name, the WOW signal. Nearly 50 years later, it remains one of the most intriguing detections in SETI history. No explanation fully accounts for it. No subsequent observation has ever detected it again despite decades of follow-up surveys. The signal's origin was traced to a region in the constellation Sagittarius. Right ascension, 19 hours 25 minutes. Declination, minus 27 degrees. That's not a point in space, it's a direction. Looking at those coordinates, you're staring toward the center of the Milky Way galaxy through dense star fields and molecular clouds. Now trace 3I Atlas's trajectory backward through space. Where did it come from, Sagittarius? Not exactly the same coordinates as the WOW signal that would be too perfect, but within 9 degrees. 9 degrees on the celestial sphere represents a huge area when you're talking about interstellar distances, but directionally it's close. Close enough that Loeb calculated the probability of random alignment at about 0.6%. Here's where it gets genuinely strange. If the WOW signal originated from 3I Atlas back in 1977, what would that require first distance? Where was the object in 1977? Tracing its trajectory backward at 58 kilometers per second, accounting for gravitational influences from the Sun and planets, places it roughly 600 astronomical units from Earth in August 1977. That's about 90 billion kilometers, deep in the outer solar system beyond the Kuiper Belt, but still technically within the Sun's gravitational influence. At that distance, transmitting a signal detectable by Big Ear would require between half a gigawatt and 2 gigawatts of power, depending on antenna gain and beam focus. That's comparable to a large nuclear power plant on Earth. Not impossible for an advanced civilization, but not trivial either. The signal was also blue-shifted by approximately 10 kilometers per second, meaning the source was moving toward Earth. 3I Atlas is currently moving toward the Sun, and by extension was moving toward Earth's general direction back in 1977. The Doppler shift matches. Not perfectly measuring precise velocities from a single 72-second signal is difficult, but within uncertainty ranges, it's consistent. If 3I Atlas transmitted the WOW signal, why Loeb suggests it might have been a radar pulse, not a communication attempt, an active sensor sweep scanning for planetary bodies in the inner solar system. When you're approaching a star system from interstellar space, knowing where the planets are is operationally valuable. You can't see them optically from hundreds of astronomical units away. They're too faint, lost in the star's glare. But if you transmit a powerful radar pulse and listen for reflections, you can detect large bodies and characterize their orbits. Earth would have reflected a tiny fraction of that pulse. Venus would have reflected some. Jupiter, despite being farther from the transmission point in 1977, would have reflected more because of its enormous size. By analyzing the timing and strength of those reflections, if you're patient enough to wait for the round-trip travel time, you could map the inner solar system's architecture. You'd know where to aim your trajectory for optimal planetary encounters decades later when you finally arrive. The problem with this hypothesis is verification. We have one detection, one 72-second signal that never repeated. Radio SETI has pointed telescopes back at that region of Sagittarius hundreds of times over the decades. Modern instruments far more sensitive than Big Ear have listened across wider frequency ranges and longer integration times. Nothing. The WOW signal remains unique, a singular event with no follow-up, no confirmation, no additional data. That uniqueness is either evidence against the signal being real extraterrestrial communication or evidence that it was a targeted transmission not meant to repeat. If you're sending a radar pulse to map a solar system, you do it once and move on. Continuous transmission wastes power. The argument cuts both ways. Skeptics say the lack of repetition suggests the WOW signal was instrumental error, terrestrial interference, or some transient natural phenomenon. Proponents say directed transmissions wouldn't necessarily repeat, and expecting them to is anthropocentric thinking based on how we do radio astronomy. 3I Atlas, arriving from roughly the same direction 48 years later, adds weight to the radar hypothesis without proving it. Coincidences happen. Sagittarius is a rich region of sky. It's where the galactic center lies, where star density is highest from our perspective, where molecular clouds and stellar nurseries create complex radio backgrounds. An interstellar object coming from that direction and a mysterious radio signal originating from that direction could be completely unrelated. But the timing is uncomfortable. If 3I Atlas left its origin system several million years ago, as seems likely given the distances and velocities involved, it would have been approaching our solar system throughout modern human history. The point when it was 600 astronomical units away, the 1970s, coincides with humanity's first serious attempts at radio SETI. We started listening just as a hypothetical probe would be close enough that radar scanning of the inner system becomes useful. That synchronicity bothers people. Either it's the most remarkable coincidence in the history of SETI, or it's not a coincidence. Add this to the statistical accumulation. Ecliptic alignment 2%, planetary encounter timing 0 to 0.5%, mass velocity combination less than 1%, wow signal directional match 0.6%. Multiply those probabilities together, and you're in parts per quadrillion territory. The probability that all these characteristics occur together by pure chance becomes so small that randomness starts feeling inadequate as explanation. But statistics can deceive. After the fact, you can make anything look improbable by carefully selecting which characteristics to measure. This is called the Texas sharpshooter fallacy, shooting bullets into a barn wall, then drawing targets around the holes to make it look like you hit bullseyes. The counter to that fallacy is defining your criteria in advance and applying them consistently. Trajectory mass composition behavior. These are fundamental observables you'd naturally examine for any interstellar visitor. The fact that all of them happen to be in the unusual tail of their probability distributions isn't a case of selecting convenient facts. It's the object itself being consistently weird across independent measurements. Natural explanations exist for each anomaly individually, but explaining all of them simultaneously requires compounding multiple rare conditions, which becomes less parsimonious than considering a single alternative explanation. That alternative is that 3I Atlas is artificial, a probe spacecraft or technological construct sent from another stellar system to explore ours. If that's true, all the alignment anomalies resolve into expected features. The trajectory alignment is deliberate navigation. The planetary encounter timing is mission planning. The extreme mass and velocity are propulsion system capabilities. The wow signal alignment is the transmission location from 48 years ago during approach. One hypothesis, multiple predictions confirmed. That's how Occam's razor is supposed to work. The simplest explanation, meaning the one with fewest independent assumptions, is preferred, but extraordinary claims require extraordinary evidence. Statistical anomalies, however improbable, aren't the same as physical proof. We need observations that can't be explained naturally, even in principle. Radio transmissions, resolved surface structures showing manufactured features, trajectory changes that can't result from outgassing or radiation pressure, active deployment of secondary objects, something definitive that breaks the ambiguity. November and December will provide opportunities for exactly those observations. And if we find them, the alignment question becomes more than statistical curiosity. It becomes the first clue that something out there planned this encounter long before we knew to look for it. Avi Loeb developed his scale for interstellar objects specifically because 3I Atlas demanded it. Before this object appeared, the framework didn't exist. There was no standardized way to quantify how unusual an interstellar visitor might be, no metric for assessing technological probability. Loeb created a 10-point scale where 0 represents definitely natural, 10 represents definitely artificial, and the middle ranges capture varying degrees of anomaly and uncertainty. 3I Atlas currently ranks at 4. That's not a guess or intuition. It's a calculation based on 8 specific anomalies, each of which has been assigned a probability of occurring naturally. Multiply those probabilities together, and you get a cumulative likelihood that measures how expected or unexpected the object's characteristics are if it formed through natural processes. The result places it firmly in the uncertain zone, too strange to dismiss as ordinary but not definitively artificial. Let's examine each anomaly systematically. Anomaly 1. Trajectory. Alignment. 3I's Atlas approaches the Sun on an orbital plane inclined only 5 degrees from the ecliptic. The ecliptic isn't a physical structure. It's the plane defined by Earth's orbit, and by extension, the approximate plane where most solar system planets orbit. Interstellar objects have no connection to that plane. When they're ejected into interstellar space, their trajectories are randomized by gravitational interactions. Some go prograde, matching their parent system's rotation. Others go retrograde. Inclinations span the full range with no preference for any particular value. For 3I Atlas to arrive aligned within 5 degrees by pure chance requires specific geometry. Of all possible approach vectors from interstellar space, only about 2% align that closely. Not impossible 2 in 100. But the first statistical oddity. Anomaly 2. Planetary encounter timing. 3I Atlas passes within tens of millions of kilometers of Mars in early October, Venus in early November, and Jupiter in March 2026. Close approaches to multiple planets during a single pass are rare. Most interstellar objects either miss everything or encounter one body by chance. The probability of arriving at just the right time to pass near 3 major planets is about 0.005%, 5 in 100,000. Combined with trajectory alignment, you're now at 2 unusual conditions happening simultaneously. The product of 2% and 0.005% is 0.0000001%. 1 in a million, and we've only covered 2 anomalies. Anomaly 3. Extreme mass and velocity. 3I Atlas is enormous compared to other interstellar visitors. Oumuamua was maybe a few hundred meters across with mass in tens of thousands of tons. 2I Borisov slightly larger but still measured in low millions of tons. 3I Gar Atlas with minimum diameter of 5 kilometers and mass exceeding 33 billion tons outweighs both predecessors by factors of thousands to millions. It also moves faster. Oumuamua entered at about 26 kilometers per second hyperbolic excess velocity. Borisov at 32 kilometers. 3I Atlas arrives at 58 kilometers. Not only is it more massive, it's carrying more kinetic energy by huge margins. The combination of extreme mass and high velocity is uncommon. Most massive objects would be gravitationally bound to their parent stars. Only rare ejection events produce massive objects with high velocities. The probability of detecting one during the brief window when humanity has the technology to identify interstellar visitors is well below 1%. Anomaly 4. Composition, nickel without iron. KK Observatory spectroscopic analysis showed prominent nickel emission lines without corresponding iron lines. That ratio is wrong for natural objects. Nickel and iron are sister elements formed together in stellar nucleosynthesis and found in similar ratios throughout the universe. Rocky bodies show iron alongside nickel when you analyze their spectra. Industrially produced nickel alloys deliberately concentrate nickel while minimizing iron because of useful properties. Finding that signature in a comet is extraordinarily rare. The probability is below 1%. Anomaly 5. Inverted water content. James Webb measurements showed 3I's Atlas has only 4% water by mass in its outgassing. Most comets are primarily water ice with smaller amounts of other volatiles. Solar system comets typically show water accounting for 70 to 90% of outgassing. Carbon dioxide dominates, instead making up 87% of observed volatiles. That inverted ratio suggests either extremely cold formation environment or unusual surface composition. The probability of encountering an interstellar comet with such unusual composition is likely under 5%. Anomaly 6. Extreme negative polarization. Very large telescope observations showed extreme negative polarization. Light scattered from the coma had wave orientation parallel to the scattering plane rather than perpendicular. This behavior is almost unprecedented in comets. The dust particle size distributions and compositions required to produce it are very specific. Natural comet dust tends to have wide size ranges and mixed composition producing positive polarization. Finding the exact conditions for negative polarization in a natural comet coma is extremely unlikely. The VLT team assessed probability at below 1%. Anomaly 7 high density from non-gravitational analysis. Analysis of over 4,000 positional measurements showed no detectable deviation from purely gravitational motion, despite confirmed outgassing of 25 kilograms per second. For active comets, outgassing creates recoil forces that push the nucleus off its gravitational trajectory. The lack of any deviation means either perfectly symmetric outgassing or extremely high mass. Perfect symmetry is inconsistent with observed asymmetric features, so the object must be at least 33 billion tons, about 1,000 times more massive than 2I Borisov, despite being only a few times larger. The implied density is much higher than typical comets, suggesting consolidated solid structure rather than porous rubble. The probability of such high density in a comet is below 1%. Anomaly 8. Wow signal. Directional alignment. 9-degree directional match with the 1977 Wow signal location with 0.6% random probability. On its own, this is the weakest anomaly. 9 degrees is a large uncertainty cone in interstellar space, but in context with the other 7, it adds another layer of statistical improbability. The cumulative calculation multiply all 8 probabilities together: 2% trajectory alignment, 0.005% planetary timing, 1% mass-velocity combination, 1% nickel-iron ratio, 5% water composition, 1% polarization, 1% density, 0.6% Wow alignment. The cumulative probability is less than 1 in 10 or more 16, 1 in 10 quadrillion. To put it differently, if you observed 10 quadrillion random interstellar objects, you'd expect to see one with this combination of characteristics purely by chance. Now there's a statistical trap here. After the fact, you can make anything look improbable. If you carefully select which characteristics to measure and which probabilities to multiply, you can create seemingly impossible odds for any object. This is the Texas sharpshooter fallacy. The counter is to define criteria in advance and apply them consistently. Loeb's scale attempts to do that. The 8 anomalies weren't cherry-picked after discovering they were unusual.
They're the kind of parameters you'd naturally examine for any interstellar visitor. Trajectory, mass, composition, behavior, fundamental observables. The fact that all of them happen to be in the unusual tail of their probability distributions isn't selecting convenient facts. It's the object itself being consistently weird across independent measurements. That's why 3I Atlas ranks at 4 on the scale. It's not one bizarre characteristic that might be a fluke. It's 8 independent characteristics, all pushing toward the low probability end. Natural explanations exist for each one individually, but explaining all of them simultaneously requires compounding multiple rare conditions, which becomes less parsimonious than considering a single alternative explanation. The alternative is that 3I Atlas is artificial, a probe spacecraft or technological construct sent from another stellar system to explore ours.
If that's true, all 8 anomalies resolve into expected features: trajectory alignment, deliberate navigation, planetary timing, mission planning, mass velocity, propulsion capabilities, nickel ratio, materials engineering low water, surface coating, mimicking comet activity, polarization, surface coating properties, high density, solid manufactured structure, Wow signal, 1977 transmission during approach. One hypothesis, 8 predictions confirmed. That's how Occam's razor works. The simplest explanation, meaning fewest independent assumptions, is preferred. 8 separate unusual natural conditions versus 1 exotic artificial origin. The artificial hypothesis is simpler in that sense, even though it sounds more extraordinary. But extraordinary claims require extraordinary evidence. Statistical anomalies, however improbable, aren't the same as physical proof. Ranking at 4 means uncertain, could be natural, could be artificial. The data doesn't force a conclusion either way. If post-perihelion observations show continued natural comet behavior, the ranking drops to 2 unusual but probably natural. If observations show impossible natural behavior, controlled maneuvers, obvious technological signatures, the ranking rises toward 10. We're in the middle, suspended between mundane and profound explanations. The 8 anomalies guarantee 3I Atlas is noteworthy. Whether it's noteworthy as the weirdest comet we've ever seen or noteworthy as first contact with extraterrestrial technology depends on data we don't have yet. December's observations will push the ranking one direction or the other. Until then, rank 4 is where it sits, a number that says we genuinely don't know what we're looking at, and that uncertainty matters. The International Asteroid Warning Network doesn't make announcements lightly. Established under United Nations coordination in 2013, IAWN exists for one purpose: to detect, track, and characterize objects that might pose collision threats to Earth. Near-Earth asteroids, comets on intersecting orbits, anything with even remote chance of impact gets flagged, analyzed, and monitored until its trajectory is fully understood. It's a global collaboration involving space agencies, observatories, and research institutions across dozens of countries. When IAWN issues a campaign notice, it means something has triggered their threat assessment protocols. On October 21, 2025, the same day 3I Atlas entered solar conjunction, IAWN released an editorial notice through the Minor Planet Center. The announcement declared a coordinated observation campaign targeting 3I Atlas running from November 27th through January 27th, 2026. This marks the first time in IAWN's history that an interstellar object has been designated for a planetary defense campaign. Read that again carefully. Planetary defense, not scientific curiosity, not routine monitoring of an interesting visitor. Defense. The language in the announcement attempts diplomatic phrasing describing the campaign as an exercise to improve astrometric techniques for challenging targets like comets with extended coma and complex morphology. They frame it as a training opportunity, a chance for the global observing community to practice extracting accurate positional measurements from difficult objects. But the subtext is impossible to miss. IAWN doesn't organize 2-month campaigns for objects that pose zero threat. 3I Atlas will pass Earth at 1.8 astronomical units, about 269 million kilometers. That's roughly 700 times farther than the Moon. There is no collision risk. None. The object's trajectory is hyperbolic, meaning it's not even gravitationally bound to the Sun. It's passing through and leaving. So why is the Planetary Defense Network mobilizing resources typically reserved for potentially hazardous asteroids? The announcement mentions specific technical challenges. Comets present unique difficulties for astrometry because their coma and tails can pull centroid measurements off the nucleus position. When you measure where a comet is, you're actually measuring the center of light, which might be offset from the physical nucleus by thousands of kilometers if outgassing is asymmetric. This creates errors in trajectory predictions. Fair enough, that's a real problem for comet tracking. But IAWN has never before organized a campaign to address this issue. They've tracked hundreds of comets over the years without needing coordinated international efforts to improve measurement techniques. The timing is also revealing. The campaign begins November 27th, exactly 1 month after perihelion. That's when 3i Atlas will be far enough from the Sun for optimal observation, but still close enough to Earth that parallax measurements from different locations provide good baseline for distance determination. The campaign ends January 27th, giving a full 2 months of intensive tracking as the object moves away from the inner solar system. 2 months of coordinated observation involving dozens of facilities worldwide, all focused on an object that poses no collision threat. ION's announcement includes another unusual element. They're requiring registration and workshop attendance for participation. If you want to join the campaign, you must register by November 7th and attend a technical workshop on comet astrometry techniques. Only participants who complete the workshop can contribute observations to the official dataset. This level of vetting is unprecedented for IAWN campaigns.
Typically, they welcome data from any qualified observer. The more telescopes watching, the better the trajectory solution. Restricting participation suggests they want tight control over who contributes data and how that data is analyzed. 3 days before IAWN's announcement on September 30th, Avi Loeb submitted a white paper to the United Nations in collaboration with colleagues Omar El-Dadi and Gershon Tenenbaum. The paper, titled Advancing Interstellar Science, advocated for exactly what IAWN is now doing: coordinated global observation of interstellar objects to maximize coverage and ensure optimal scientific monitoring. Loeb's argument is direct. If interstellar visitors could potentially carry alien technology even with low probability, the implications for humanity are significant enough that we should treat such objects with the same seriousness as potential impact threats.
The white paper uses the term black swan events, situations with small probability but enormous consequences. Standard risk assessment might dismiss low probability scenarios. But when the potential outcome includes first contact with extraterrestrial intelligence or worse, hostile technology entering our planetary system, probability calculations change. You don't wait for certainty, you act on precaution. IWN's campaign launched less than a month after that white paper reached UN committees. That suggests someone took the argument seriously. This creates an interesting dynamic. Publicly, space agencies maintain that 3i Atlas is a natural comet showing unusual but explainable characteristics. NASA's official statements emphasize there's no threat to Earth, and the object will pass safely through the solar system. Tom Statler, NASA's lead scientist for small bodies, has stated on record that all data point to comet classification. The European Space Agency echoes this position.
Everything is routine, nothing to worry about. But behind that public messaging, IAWN, a UN-backed organization specifically tasked with planetary defense, is organizing the most comprehensive observation campaign ever directed at an interstellar object. They're doing it during the exact time window when, if the object were going to do something unexpected, it would become evident. They're restricting participation to vetted observers who've completed specialized training, and they're coordinating with international space agencies to ensure global coverage, meaning no matter where 3i Atlas appears in the sky, multiple facilities will be tracking it simultaneously. The disconnect between public messaging and institutional behavior is stark.
If 3i Atlas is just an interesting but harmless comet, why mobilize planetary defense resources? If there's even a small concern that it might be something else, why downplay that possibility publicly while ramping up monitoring privately? One explanation is institutional caution without alarm. Space agencies learned from past communication failures that premature announcements create public panic disproportionate to actual risk. Remember, asteroid Apophis, discovered in 2004 with initial impact, probability calculations showing small but non-zero chance of Earth collision in 2029. Media coverage created widespread concern before refined observations showed the impact risk was essentially zero. Agencies don't want to repeat that pattern. Better to monitor intensively, gather definitive data, and only make public statements when conclusions are certain. But that explanation assumes the risk is impact-related. 3I Atlas won't hit Earth. The trajectory is unambiguous on that point. So what risk is IAWN concerned about? The campaign announcement doesn't say. It talks about improving astrometry techniques. It mentions the scientific value of studying rare interstellar visitors. It frames everything as opportunity rather than threat. Yet the structure of the campaign, the resources being deployed, the coordination level all suggest this is being treated as more than scientific curiosity. Loeb's white paper offers a possibility that official channels won't articulate. If 3I Atlas releases secondary objects at perihelion mini-probes or fragments that separate from the main body, those secondaries could be on trajectories that bring them closer to Earth than the primary object. Detecting and tracking such secondaries requires coordinated observation with high-cadence monitoring. You need multiple facilities watching, so that if something separates, it's documented immediately and tracked continuously until its trajectory is fully characterized. The IADWN campaign is designed exactly for that scenario. 2 months of intensive monitoring, multiple observation sites providing redundant coverage, standardized measurement techniques ensuring all positional data is comparable. Workshop training to make sure everyone knows how to distinguish real objects from artifacts or noise. It's a deployment protocol for detecting and tracking unexpected secondaries. Another aspect rarely discussed publicly is the possibility of trajectory changes post-perihelion. If 3I Atlas executes maneuvers during the hidden period behind the Sun, those maneuvers might redirect it toward closer Earth approach than currently predicted. The probability is low. But if you're doing threat assessment, you don't ignore low-probability scenarios with high-consequence outcomes. Tracking the object intensively immediately after perihelion lets you detect trajectory changes within days rather than weeks, providing maximum warning time if the approach distance starts decreasing. IWN's involvement also signals something about internal discussions at government levels. The organization reports to the UN Committee on the Peaceful Uses of Outer Space. For them to approve and resource this campaign required briefings, presentations, and consensus among member states that the monitoring is justified. Whatever data or analysis convinced those committees isn't public. We see the output, the campaign itself, but not the input, the evidence or arguments that motivated the decision. The campaign also serves a diplomatic function. By involving observatories from many countries, IAWN ensures that data isn't controlled by a single nation or agency. If discoveries occur, they're immediately international shared among all participants. This prevents scenarios where one country monopolizes information about something potentially significant. It's transparency through collaboration, making sure no one can claim secret knowledge or hide important findings. For the public, IAWN's campaign sends a mixed message. On one hand, it's reassuring that serious institutions are monitoring 3I Atlas carefully. If there were genuine concern about threat, we want planetary defense systems engaged and watching. On the other hand, the very fact that they're engaged raises questions about why. What do they know or suspect that justifies this level of attention? The answer is probably more mundane than conspiracy theories suggest. 3I Atlas is genuinely unusual. The combination of anomalies, whatever their ultimate explanation, merits close observation. IAWN seizing the opportunity to practice coordinated monitoring makes operational sense. When a real threat emerges someday, having trained international teams experienced in rapid campaign deployment will be valuable. 3I Atlas, threatening or not, provides that training opportunity. But training exercises usually get announced as training exercises. The language IAWN uses, the structure of the campaign, the restriction on participation, all suggest this is more than practice. It's operational. They're treating 3i Atlas as something that requires active monitoring under protocols normally reserved for objects we're worried about. November 27th is when the campaign officially begins. Between now and then, 3i Atlas completes its perihelion passage, emerges from solar conjunction, and becomes observable again. The first campaign observations will document whatever state the object is in post-perihelion. That initial dataset becomes the baseline for everything that follows. If the object shows changes from pre-perihelion observations, differences in brightness, spectrum, morphology, trajectory, those changes appear immediately in the campaign data. IAWN is positioning dozens of telescopes to watch the reveal. They're coordinating schedules to ensure continuous coverage. They're training observers to look for specific signatures that might indicate something beyond normal comet evolution. And they're doing all of this under the framework of planetary defense language that implies they consider 3i Atlas relevant to Earth's safety even though its trajectory poses no impact risk. What they know that we don't remains unclear. What they suspect but won't say publicly is easier to infer. And what they'll find when intensive monitoring begins in late November might finally answer the question that's been growing louder since July. Are we watching the most unusual comet in history, or are we watching something else entirely? Brandon Biggs didn't set out to become known as the prophet who predicted the Trump assassination attempt. But in April 2024, months before the July 13th shooting at a Pennsylvania rally, Biggs recorded a video describing a vision. He spoke about seeing a bullet fly past Donald Trump's ear so close it burst his eardrum. He described the chaos, the blood, Trump surviving but injured. When the actual attempt happened in July, matching those details with eerie precision, Biggs went from obscure Christian pastor to viral phenomenon overnight. That track record, that one incredibly specific prediction that came true, gives his subsequent visions a weight they might not otherwise carry. When someone calls something that unlikely, that detailed, you pay attention to what they say next. Even if you're skeptical of prophetic claims in general. What Biggs said next in a video released in mid-October was about aliens, specifically about a giant mothership arriving on Earth. In his vision, Biggs described seeing a massive alien craft flying over the Vatican and Mayan temples in Mexico, not two ships, one. He emphasizes that detail. He asked in the vision whether there were multiple craft and was told, no, just one enormous vessel. The ship moves slowly across the ocean in full view. Everyone sees it. It's broadcast on television worldwide, creating global panic. Then smaller craft emerge from the mothership. Biggs describes them as balls of light, mini-ships that scatter from the primary vessel. The timing of this video released in mid-October, as 3i Atlas approached perihelion, triggered immediate speculation online. Social media exploded with theories connecting Biggs's vision to the interstellar object. Forums lit up with discussions comparing his description of a mothership releasing smaller probes to Loeb's hypothesis about 3i Atlas potentially deploying mini-spacecraft at perihelion. The parallels are striking. Biggs talks about one large vessel releasing multiple smaller objects. Loeb talks about a mothership scenario where 3i Atlas, if artificial, would release mini-probes during its closest approach to the Sun. Biggs had actually mentioned this vision earlier, back in July, shortly after 3i Atlas was discovered. He described seeing little ships coming out of a larger craft, balls of light emerging from something massive. At the time, most viewers interpreted it as generic prophetic imagery, the kind of vague, apocalyptic scenario common in religious visions. But the July timing, right when 3i Atlas entered public consciousness, and the October emphasis right before perihelion, created a narrative arc that conspiracy communities found impossible to ignore. The theological framework Biggs uses is important context. He's not claiming these are benevolent extraterrestrial visitors. He frames them explicitly as demonic entities, spiritual forces using physical manifestation to deceive humanity. In his interpretation, the mothership and smaller craft are satanic deception, part of a larger end-times scenario preparing the world to accept the Antichrist. The beings aren't aliens in the science fiction sense. They're fallen angels or demons, taking forms that modern secular society will interpret as extraterrestrial. This theological lens doesn't make his predictions less interesting from a phenomenological standpoint. If you strip away the spiritual interpretation and look at just the claimed observations, flying objects, mothership releasing smaller craft, global visibility television coverage, you're left with descriptions that could apply to physical phenomena regardless of their ultimate nature or origin. Whether you interpret those phenomena as technology from another stellar system or manifestations of spiritual entities becomes a matter of worldview. The internet did what the internet does.
Within hours of Biggs's October video, circulating edited versions appeared linking his statements directly to 3I Atlas. Some added images of the object from Hubble and JWST. Others overlaid orbital diagrams showing its trajectory. The synthesis created a narrative where a Christian prophet and a Harvard astrophysicist were independently describing the same event from different conceptual frameworks. Loeb talks about Oberth maneuvers and mini-probe deployment. Biggs talks about motherships and balls of light. The vocabulary differs, but the core scenario aligns. Mainstream media largely ignored this connection. Prophetic visions don't make comfortable material for science journalism, but alternative media, conspiracy-focused platforms, and religious communities amplified it aggressively. For certain audiences, the combination of Biggs's credibility from the Trump prediction plus the scientific anomalies surrounding 3I Atlas created a perfect storm of validation.
Here was spiritual warning confirmed by empirical observation, or depending on your perspective, here was interesting astronomical data being wrapped in apocalyptic religious interpretation. The balls of light detail is particularly interesting because it echoes descriptions from UAP encounters. Unidentified aerial phenomena reports, especially from military personnel, frequently describe luminous spheres that move in ways inconsistent with known aircraft. These aren't necessarily connected to 3I Atlas, but the descriptive overlap between Biggs's vision and existing UAP reports added another layer of cross-validation for those predisposed to see connections. Skeptics point out that prophetic visions are inherently unfalsifiable until they either happen or don't. Biggs can describe anything, and if it doesn't occur, supporters will argue the timeline was misinterpreted or the prediction was conditional on human response. If something vaguely matching the description happens, it gets counted as a hit, even if details are loose. The Trump assassination prediction is the exception, specific enough and accurate enough that explaining it away requires uncomfortable contortions. But one accurate prediction doesn't validate all subsequent claims. There's also the problem of influence. Biggs has access to the internet. He follows news. By October 33rd, Atlas was headline material. Loeb's mothership hypothesis had been discussed in major publications. Could Biggs have absorbed that information consciously or unconsciously and incorporated it into his religious framework? Vision and imagination are hard to distinguish, especially when both draw from the same informational environment. Claiming divine revelation about something you've read about, even if you don't consciously remember reading it, is a well-documented psychological phenomenon. But then there's the July mention.
Biggs described ships and balls of light back when 3I Atlas was barely known outside specialist circles. Loeb hadn't yet published detailed papers on the technological hypothesis. The mothership scenario wasn't mainstream discussion. If Biggs was unconsciously pulling from media coverage, what coverage existed in early July that would have planted those specific images? The object had just been discovered. Initial reports called it a comet. Interesting, because it was interstellar, but not yet laden with anomaly discussions or technological speculation. That timing issue is why some take Biggs more seriously than they otherwise might. Either he got very lucky, guessing that an interstellar object would become associated with mothership theories, or he had genuine insight through whatever process produces his visions, psychological, spiritual, or otherwise. The Trump prediction makes lucky guessing harder to accept as explanation.
From a sociological perspective, Biggs represents something important, regardless of prophetic accuracy. He's a conduit through which scientific uncertainties get translated into religious narrative. 3i Atlas, with its statistical anomalies and technological hypothesis, creates space for apocalyptic interpretation. People looking for signs of end times see a mysterious object from the stars, possibly releasing probes into our solar system, as exactly the kind of event that would precede major prophetic fulfillments. The beast system, one world government, the revealing of hidden truths. All classic eschatological themes find purchase in interstellar visitor scenarios. This isn't new. Every major astronomical event in history gets interpreted through religious frameworks. Comets were omens in ancient times. Eclipses signaled divine displeasure. Modern UFO phenomena get absorbed into both secular and religious explanatory systems. 3i Atlas is just the latest celestial occurrence being pulled into those interpretive structures, amplified by social media and the genuine scientific puzzles the object presents. What makes this case unusual is the convergence. You have a prophet with demonstrated credibility from a recent specific prediction. You have a scientific hypothesis from a respected astrophysicist that uses mothership language. You have timing synchronicity, where the vision details align with a perihelion window when deployment would theoretically occur. And you have an object that's genuinely anomalous enough that even skeptical scientists admit it's worth serious attention. That convergence doesn't prove anything about prophecy or alien visitation or spiritual manifestation. It proves that when reality gets weird enough, multiple explanatory frameworks start pointing at the same phenomena. Scientists say probe deployment. Prophets say demonic manifestation. Both could be wrong. Both could be partially right in ways that don't contradict each other. Arthur C. Clarke's third law, sufficiently advanced technology, is indistinguishable from supernatural phenomena. If 3i Atlas does release objects at perihelion, if we observe secondary spacecraft emerging from the primary body, how will different communities interpret that? Scientists will analyze trajectories, spectrometry, propulsion signatures. They'll try to determine origin-purpose capabilities. Religious communities will see fulfillment of prophecy evidence of spiritual warfare signs of approaching end times. Both interpretations will be internally consistent within their frameworks. Both will feel validated by the observations. This is where epistemology matters. How do we know what we know? Science relies on observation, measurement, repeatability. Religion relies on revelation, scripture, spiritual discernment. When both point at the same event and say something significant is happening, but describe it in incompatible vocabularies, resolution becomes difficult. You can't prove spiritual entities aren't using physical craft to manifest. You can't prove advanced aliens aren't being misinterpreted as angels or demons. The frameworks are incommensurable in important ways. What we can say is Biggs described a scenario using language from his religious tradition that overlaps significantly with scenarios described by scientists using secular language. Whether that overlap results from shared underlying reality, from influence and information contamination, or from pure coincidence, doesn't change the sociological impact. Millions of people across religious and secular communities are now watching 3i Atlas with heightened attention, expecting something dramatic. That expectation matters. If nothing unusual happens, if the object completes its perihelion passage and continues on a purely gravitational trajectory, showing normal comet evolution, both communities will experience disappointment. Scientists who allowed themselves to consider the technological hypothesis will return to conventional explanations. Religious communities will adjust prophetic timelines or reinterpret the vision as symbolic rather than literal. Life continues. But if something does happen, if we observe deployments, maneuvers, transmissions, anything that confirms the mothership scenario in scientific terms, the religious interpretation gains immense cultural power. Biggs will have predicted not just one unlikely event, but two: the Trump assassination and the alien arrival. That track record would make him one of the most credible prophetic voices in modern history. Whether you accept his theological framework or not, you'd have to acknowledge he somehow accessed accurate information about future events. The December observations will test this directly. If mini probes separate from 3I Atlas and begin independent trajectories toward Earth or other planets, we'll know within days. Telescopes worldwide are positioned to watch. The IAWN campaign specifically looks for exactly this signature. We're not going into December blind. We're going in with the most comprehensive monitoring effort ever directed at an interstellar visitor. Biggs's vision adds a narrative layer to that monitoring. He's given the observation human drama and spiritual stakes. Whether his interpretation is correct or not, he's ensured that when 3I Atlas emerges from behind the sun and astronomers report their findings, those findings will be filtered through multiple interpretive lenses simultaneously. The story isn't just scientific anymore. It's cultural, spiritual, existential. And maybe that's appropriate. If we are watching something that challenges our understanding of our place in the cosmos, whether through technological contact or other means, it should engage more than just our scientific institutions. It should engage our spiritual traditions, our philosophical frameworks, our deepest questions about meaning and purpose. 3I Atlas has become a Rorschach test for humanity's diverse ways of making sense of the unknown. What we see in it says as much about us as it does about the object itself.
October 21st, 2025. Something in the cosmos deviated from the path we predicted. Not by meters, not by thousands of kilometers, by over 1 million kilometers, and growing with every hour we watched. We've spent this evening examining what that deviation means. We've looked at the numbers, trajectory anomalies, brightness paradoxes, composition ciphers. We've explored the geometric patterns in plasma that shouldn't exist. We've traced the anti-tail that pointed the wrong way, then flipped at exactly the moment our physics predicted it would, or exactly the moment a spacecraft would reverse its engines. We've counted the statistical improbabilities, 8 anomalies each, explainable alone, all accumulating into odds, measured in parts per quadrillion. We've seen how planetary defense networks activated for an object that poses no collision risk. We've heard how prophets and physicists independently describe the same scenario using different vocabularies.
And we've sat with the uncomfortable reality that behind the sun for 8 days, in late October, something either obeyed the ancient laws of ice and stone or rewrote them. Let me tell you what we know for certain. 3I Atlas is real. It's interstellar. It's behaviorally unusual across multiple independent measurements. The trajectory deviations are documented by numerous observatories. The brightness paradox persists despite confirmed active outgassing. The composition shows ratios inconsistent with natural cosmic abundances. The polarization measurements sit in statistical regions where comets rarely venture. The object arrived aligned with our planetary plane within margins that make mission planning easy and random chance uncomfortable. It timed its arrival to pass near Mars-Venus and Jupiter encounters that would give any probe comprehensive access to the inner solar system. And it may or may not have announced itself 48 years ago with a 72-second radio transmission that remains the most intriguing, unresolved signal in SETI history. These are facts, measurements, observations that multiple independent groups have verified. What we don't know is what they mean. Natural explanations exist for every piece. An interstellar comet formed under conditions vastly different from our solar system's comets. Unusual chemistry from exotic formation environments. Magnetic remnants from its birth nebula. Viewing geometries that make brightness predictions difficult. Dust properties we haven't encountered in solar system comets. Stack enough unusual but possible natural conditions, and you can explain 3I Atlas without invoking anything extraordinary. But that stacking comes at a cost. Each explanation stands alone. Each requires its own special conditions. The parsimony that science values the preference for simplicity starts to strain when you need 8 independent rare circumstances to account for 8 linked anomalies. The alternative explanation is simpler. In one sense, a single exotic origin rather than multiple natural rarities. If 3I Atlas is artificial, a probe spacecraft or autonomous explorer, all 8 anomalies resolve into expected features of an engineered system operating in our solar system. But that explanation is more complex in another sense. It requires accepting that we're not alone, that intelligence exists beyond Earth, that something out there built a machine, pointed it at our star, and sent it across the galaxy to see what it would find. That's a bigger assumption than unusual comet chemistry. So where does that leave us? We stand at a threshold, a moment where data meets mystery. November and December will bring answers. Post-perihelion observations will show whether 3I Atlas returns to predicted behavior or continues defying our models. The IAWN campaign will watch for secondary deployments. Trajectory changes anything that crosses the line from unusual to impossible. By February 2026, we'll either have confirmation that this was the strangest comet in recorded history, teaching us that interstellar space produces objects far more diverse than we imagined, or we'll have evidence that forces us to reconsider fundamental assumptions about our place in the universe. Both possibilities are profound. If it's natural, we learn that the cosmos is weirder than we thought, that our sample size 3 interstellar visitors detected ever is far too small to draw conclusions about what's typical. That formation processes we don't understand create objects that challenge our models in systematic ways. Future interstellar visitors will continue surprising us. Each one will expand our understanding of what's possible in the vast laboratory of space and time that predates our sun, our planets, our species. If it's artificial, we learn something more unsettling, that the universe remembers us. That intelligence elsewhere took the trouble to build something that would cross unimaginable distances to reach our star, that whatever sent it cared enough to look, that the cosmos isn't empty of minds capable of asking the same questions we ask, that we are perhaps for the first time in human history being studied the way we study insects under glass. Both scenarios demand we expand our intellectual horizons. Both force humility. Both remind us how much we have left to learn, but one of them changes everything else we thought we knew about being human. There's a question I want to leave you with as you drift towards sleep, a question with no easy answer, a question the universe might be asking us right now as 3I Atlas emerges from behind the sun and heads toward its closest approach to Earth. When an object from the stars arrives in our planetary system during the exact years humanity develops the technology to detect it, when it coincides with our first SETI protocols for physical contact, when it behaves in ways that align almost perfectly with how we would design an interstellar probe, when it passes planets with timing that would make mission planners weep with envy, when 8 independent anomalies compound into probabilities measured in quadrillions. At what point does coincidence become pattern? And at what point does pattern demand we change our assumptions about our place in the cosmos? I don't have the answer. No one does, not yet. But November is coming. December will bring 3I Atlas closer than it's been since July. Telescopes worldwide are ready. Planetary defense networks are coordinated. Scientists and prophet skeptics and believers are all watching the same patch of sky, waiting for revelation or reassurance. The universe doesn't owe us explanation. It doesn't owe us comfort or clarity. It moves according to laws we've barely glimpsed on timescales that dwarf our brief moment of consciousness. But sometimes, just sometimes, it offers us glimpses. Moments when the veil thins, when something from the vast dark arrives on our doorstep and forces us to ask whether we've been alone all this time or whether we've simply been looking in the wrong direction. 3i Atlas is that moment. Whether it's a comet or a messenger ice or intelligence, the universe has given us a gift, the gift of uncertainty, the gift of questions too large to dismiss, the gift of wonder mixed with apprehension. On October 21st, something deviated from the path we predicted, and in deviating it reminded us of a fundamental truth. The cosmos is larger, stranger, and more full of surprises than any of our certainties allow. Perhaps 3i Atlas was never passing by. Perhaps it was pausing long enough to see if we were ready to notice, long enough to see if we were brave enough to ask what happens next. The universe is not silent. It's waiting for the right frequency of consciousness to listen, and the frequency might be changing. Right now, as you close your eyes tonight, somewhere above you, an object from between the stars is completing its journey. By the time you wake, telescopes will have captured new data. Algorithms will have crunched new numbers. Scientists will be analyzing what happened during those 8 invisible days. We might wake to confirmation that the universe works exactly as we thought, or we might wake to a morning when everything changed and we just didn't know it yet. Either way, the sky that watched us for billions of years, it might finally be watching back. Sleep well. Wonder remains. And the universe, the vast, patient, ancient universe, waits to see what we do with it.